All right, here are the solutions to week 6 homework. We did lessons 5 and 6 in unit 6 this week, so a lot of sixes. A rocket is launched in the air and its height in feet is modeled by the function h. Here is a graph representing h. So we want to select all statements about the situations that are true. So looking at A there, we'll just go through them one by one and decide whether we want to circle them or not. The rocket is launched from a height less than 20 feet above the ground. That would be right here where it's launched from. This is the height axis, and so that's where it starts. So yeah, I would say less than 20 feet because that scale on the y-axis goes up by 20. Letter B, the rocket is launched from about 20 feet above the ground. I wouldn't circle that then because it's less than. Letter C, the rocket reaches a maximum height after about 3 seconds. I would agree with that. Time in seconds here, and it looks like after 3 seconds has gone by, the rocket is at its maximum height, so I would agree with that one. Letter D, the rocket reaches its maximum height after about 160 seconds. Well, remember, this is our seconds, so we don't even have 160 represented there. And the maximum height of the rocket is about 160 feet. That's true. 160 feet on the vertical axis there is the maximum height then. Number 2, a baseball travels d meters t seconds after being dropped from the top of a building. The distance traveled by the baseball can be modeled by the equation d is equal to 5t squared. And we want to complete the table and plot the data on the coordinate plane. So I'm going to recommend that we use our table making capabilities in Desmos. And so let's take this equation over to Desmos app and we'll fill it in. I'm going to fill in y is equal to 5x squared just to make it easier on the app. So let's go over here and we'll type that in. Y is equal to 5x squared. Looks like this. And then remember, we can go up here and use the little gear button to find a table for that function over in our area here. And we do not care about negative time here. So we're just going to look at, I'm going to delete these ones. And then I'm going to start at 0 and go up by 0.5. So I'm going to, I'm going to put in a 0.5 after 0. And then I'm going to go after 1. I'm going to put in a 1.5. And then up to 2. And then I'm going to go 2.5. And then up to 3. And then 3.5. It starts autofilling for me. So here's my graph, and notice we're only on the right side of that parabola. We're talking about distance fallen. So as time goes by, the distance that the, was it a rock? Or yeah, I think a rock has fallen, increases at an increasing rate there. So it's not a constant fall. So let's screenshot this and bring it over to Notability, and then we can just plop it in there. I want to adjust it. I think I'll put it over the other graph, and then we can fill this into 0, and at 0.5 it's fallen 1.25 meters, and then after 1 second it has fallen 5 meters. After 1.5 seconds it has fallen 11.25 meters, and after 2 seconds it has fallen 20 meters. So is the baseball traveling at a constant speed? Explain how you know. No, it is not. We know because the distance it's fallen increases at an increasing rate. So it's not linear. For example, what we mean by that is from 0 to 0.5 seconds, it's fallen 1.25 feet. And then from 5.5 seconds to 1 second later, it's fallen much more than that. So 3.75 feet. And this distance that it falls keeps increasing. So it's not a constant speed. From 5 to 11.25, make sure I don't make any mistakes here, it's fallen 6.25 feet. So for each half second after it's dropped, the rate that it's falling is increasing, and it's not a constant rate or not a constant speed. Number 3, a rock is dropped from a bridge over a river. Which table could represent the distance in feet fallen as a function of time in seconds? So this one, as we look, each one of these tables goes up by 1 second at a time. And the rock here falls 48, then 48 more feet, and then 48 more feet. That's a constant rate. And so this would be out. That's not how gravity works for us. Table B, it looks like it increases by 16 here. And then it increases by a lot more than 16. Got a 48 here. And so this could be the one. It's increasing at an increasing rate. And so here we go up 80. So yeah, I think table B, looking at table C and D, distance fallen is a positive increasing value, because as time goes on, the distance fallen increases. So neither of these tables increase, so that would be out. So I would circle table B here. And let's move on to those problems from lesson 6. So we have the height of a diver above the water is given by this function here, where t is measured in time, is time measured in seconds, and h of t is measured in meters. So we're talking about time and height. Select all statements that are true. So let's just go through them again. The diver begins 5 meters above the water. Remember, that is, this is our initial height in these time height functions, so this is a no. The diver begins 3 meters above the water is true, though. The function has a 1 0 that makes sense in this situation. Right, if the diver begins 3 meters above the water, we're just interested in that particular part of the parabola. So it might have a 0 over here, but we don't really care about that. We're just interested from here to the rest. And so the water height would be here, where he enters the water. So this is the only 0 that we're interested in looking at. So that would be a true statement. Letter D then would be a no, because we don't care about this negative one over here, the one that's happening here. Here's where the diver is standing, and that's his height as time goes on from that moment on. So that's the only part of the curve that we're looking at. So that's a no. E, the graph that represents H, starts at the origin and curves upward. No, it doesn't start at the origin. The origin is here, so that's a no. And F, the diver begins at the same height as the water level, and that's a no. He's on a board up here. So B and C would be the only true statements for number 1. Number 2, the height of a baseball in feet is modeled by the function h given by the equation h of t equals 3 plus 60t minus 60t squared. And this time we're talking about feet, and h is the function and t is the time again. So h is the height and t is the time. So about when does the baseball reach its maximum height? So when would be along here. And so we want to look at what time does it reach its maximum height. Well, right about there is the maximum height. So I'd say a little less than 2 seconds is when it reaches its maximum height. And about how high is the maximum height? Well, it looks like it's about 60 feet. So we could say about 60 feet. And letter C, about when does the ball hit the ground? And so here it is over here hitting the ground. It started higher than the ground, just leaving someone's hand there, but it hits the ground over here less than 4 seconds later. So less than 4 seconds after it's thrown. The next one requires technology, and so we've got 2 rocks launched straight up into the air, and the height of the rock A is given by the function f there, and I'm just going to write these down. G is given by, or the rock B is given, the height of rock B is given by the function g. So let's look at each of those. So we'll go over here to Desmos and get rid of that table from the previous problem and type in each of these functions. You can type them in as functions. I'll show you how to do that. You just go over to the the keyboard, and you can type in f of x using your parenthesis, your left parenthesis, then an x, and then use the up arrow to get the right parenthesis. And then type equals, and we'd have 4 plus 30x, and let's see, minus 16x squared. So that green parabola is representing rock A, and then rock B, we can call that g of x. So we'll go over here and type into g, left parenthesis, then an x, then we'll go get the right parenthesis and go back over to our numerical keyboard. So we have g of x is equal to 5 plus 20x minus 16x squared. And so there they are, both of them. And the question was, let's just bring this over to Notability. The question was, use the graphing technology to graph both equations and determine which rock hits the ground first. So we'll just kind of take a look at it here. It looks like the orange one hits the ground first. It's crossing the x-axis, which would be height of 0, so that's hitting the ground. It crosses the x-axis before the function f does, the rock A. Rock A takes a little bit longer, and so rock B hits the ground first. And you know because B crosses the x-axis before rock A does. Number 4, each expression represents an object's distance from the ground in meters as a function of time in second, time t in seconds. So we have object A with this equation and object B with this equation. And for letter A there it says which object was launched with the greatest vertical speed. Remember, this is our velocity, initial velocity. So object B would be the one that was launched with the greatest vertical speed. And which object was launched from the greatest height? Remember, this term out here, that last constant term, is our initial height. And so that would be object A then started at 50 meters and B started 25 meters. And that's it. I hope this helped.